My name is Martina Flörke, and I'm based at the Center for Environmental Systems Research, which is a center at the University of Kassel in Germany. And first, I have to admit, I'm not an economist, so there will not be so much economics into the modeling that I would like to present. However, I'm more than convinced that it would be needed to link the water model that has been developed at our center and is still improved there, would like to have a link to the economics and, let's say, to other kind of models as well in an integrative way. Nevertheless, what I would like to present today is water and energy and the critical link between the two embedded in the SDG context, which is, let's say, the topic of the whole session today. And I would like to bring you back to the different goals, starting with goal 6, which is dealing with water and with the overall goal of ensuring water, the access to water and sanitation for all, and the different, here it is, the pointer, and the different targets being set, like the drinking water for all and the ambient water quality, increasing water use efficiency, and so on. And on the other side, we have, for example, goal 2, end of hunger, which is related, let's say, to the agricultural sector, and goal 7, for example, ensuring the access to affordable, reliable, sustainable, and modern energy for all. And we would like to achieve, as much as we can, out of the sustainable development goals. However, we may already expect that there might be the occurrence of conflicts and trade-offs between achieving the different goals. We have heard quite a lot about the developments, let's say, on food, water, and energy, and I would like to show additional figures on that. It's quite likely that, water withdrawals will increase in the future due to the increase in population, due to a wealthier society, due to demanding for more food and demanding for more electricity, for example. Thermal electricity production as an outcome of the SSP process is expected to increase for between the different SSPs, so SSP1 to SSP3, between 32 and 72% between 2010 and 2050. And we have heard already about it from the FAO report that an increase in food demand, increase for meat and cereals can also be expected, driven by socio-economic growth too. So the SDGs and the nexus, as being shown by a figure developed by Holger Hoff and presented at the Nexus conference in Bonn, centered the energy security, water supply security, and food security, which have been identified as being the key the key topics on the Rio +20 conference. So it's embedded or driven by the global trends like urbanization, population growth, economic developments, climate changes, but there were several action fields also driving. So coming from the society, economy, but also from the environment, governance is an enabling factor as well, which then finally may lead us to new innovations. So we know that, for example, between the water supply and energy security, which I would like to focus on today, that there are the critical interlinkages and also interdependencies between the two. So we can expect trade-offs, competition, but also synergies that we need to address and identify first as well. So coming back to the water and energy access in the context of the SDGs, the situation as it is today is showing that about 700 million people do not have access to improved water, and even more, 2.5 billion people do not have access to improved sanitation. On the other side, there are also more than 1 billion people who have no access to electricity. So how to bring these two together and how to improve the situation on the water side as well as at the energy side. Water and energy and the interlinkages are given by that water is required to generate electricity, for example, hydropower, thermal energy, and so on, but also biofuels, biocropping needs water. On the other side, energy is then used for pumping and treating and the transport of water to the various consumers, as we all have already heard this afternoon. So the water requirements for energy are first in the primary energy production in terms of mining, but also for the first generation biofuels as shown in here. And then when it comes to electricity production, then we need water again for the tools itself, but also for cooling the condensers in many power locations. So the key questions that I would like to address today are where and when could water limit energy production? And will there be enough water to reach the SDG goal for energy access? And what are the impacts of energy on water under climate change conditions? And also taking into consideration other global developments. And last but not least, can we identify the trade-offs and can we develop strategies for synergies to bring the water and energy linkages forward? And you have already heard about the water gap model today in the talk that Richard gave right at the beginning. So water gap is a water modeling framework consisting of a hydrological model, water use models, and a water quality model, which are interlinked by different kind of fluxes. The model operates on a spatial resolution, which is 5 by 5 arc minutes, so on a grid cell level, in a temporal way on daily incomes and outputs, depending on the model. In terms of water quality, the temporal resolution is monthly. So when we look at the development of the energy sector in terms of thermal electricity production and the cooling water that is needed to produce the electricity, you can see on the graph here below the development in the electricity production since 1950, but also the development in water withdrawals. And here is the water consumption, which is quite low because most of the plants use run through cooling. Nevertheless, a little bit of increase is due to the fact that a lot of power plants have been replaced by tower cooling. But the development, say in the location of the different power plants, has been tremendous over the last 60 years. So in the 1950s, you see most of the water being extracted in the developing countries, in the developed countries, but nowadays the more and more water is now extracted for cooling, for example, in India, in China, but also in some parts of Latin America. And an increase in Europe can also be seen like the increase in cooling water abstractions at the East Coast in the US. So the future of the thermal electricity production, how it will look like in the future, is given by the SSP scenarios that we used from the WAFA's Water Futures and Solutions Initiative in Luxembourg. And then we just used our modeling tool and to analyze where and when water limits energy production, and we calculated a cooling water gap. This means that we summed up the monthly water that is not being satisfied by the water availability. So in the first case, we assumed that all of the water that is available, all the renewable water that is available, can be used by the power plants at the given locations. So the RCP that we use for climate change input is, let's say, the more lower end RCP, but combined with a more sustainable SSP1 scenario. Then in the next step, we looked where and when could water-related SDGs limit energy production. So the cooling water gap now has been increased to 19 billion cubic meters because we took into consideration water for all and an ambient water quality. So water cannot be returned into the system if river discharge is above 23 degrees. And in terms of food security, we also addressed water that is used for irrigation. And for goal 15, the water for aquatic ecosystems, we accounted for environmental flows too. So in just assuming that these goals get the water as well, the cooling water gap, so to provide enough water to generate electricity, is much larger than it is if we would just consider the water, all water being available for electricity production. And this has been given here by the different management options, how I named them. And if you look at the developments for the different SSPs, you clearly see that under the management options, meaning that particularly in option 1, that we have other uses, not just only the water being available for cooling. We have to sustain environmental flows, and we have to keep the water temperature below 23 degrees. The cooling water gap clearly increases depending on the different SSPs, because SSP2 and SSP3 is demanding for more thermal electricity production compared to SSP1. So what are the trade-offs? I would like to say that the population and economic growth, they both increase the competition for water. But also climate change is a big player in that game by exacerbating competition. The risk of water scarcity leads to cooling water shortages, and higher water temperature increases the cooling water gap as well. On the other side, we have to take care of thermal pollution, which deteriorates water quality. And finally, the reduced thermal electricity production is likely to affect population and economy. But then can we transform the trade-offs into synergies? What can be the actions? And I just want to show two of, I guess, several other examples. By increasing the contribution of low-carbon energy options or the changing in consumer behavior, we are going to address several SDG goals and targets at the same time. So, for example, energy, just to ensure that all people get access. Water, to improve water quality, reduce freshwater abstractions. In terms of climate change, to mitigate CO2 emissions. For food, to produce less bioenergy crops, for example, leading to a less fertilizer input and nutrient pollution. So my conclusions from this modeling study are that it's crucial to evaluate the linkages between water goals and other SDGs. A nexus, or at least a systems approach, needs to be combined with scenario analysis to look into the future and to address the goals in the 2030s. And the identification of the critical linkages lead us to the trade-offs, and the trade-offs in turn lead us to the identification of priorities which need to be set in terms of scarcity, for example. And last but not least, getting the assessment of the trade-offs helps us to develop the strategies to transform the trade-offs into synergies. I'm quite optimistic, looking forward into the future, but I'm sure that from the modeling perspective, there are several challenges that we need to address because of the shortcomings that are also being addressed by this modeling study. So that has been my last slide, and thank you for your attention.
Well, thanks a lot, Martina, for looking at the interlinkages, this nexus. And thanks also for looking at some of the quantified trade-offs between, in particular, energy and water targets. I would like to allow for one question, one statement here from the floor. Thomas has one.
I was struck by your, when you added irrigation requirements and the temperature constraint and so on, all of a sudden the map got very intense. So up to that point, I was kind of relaxed, and then that got very intense. I guess I had two questions in that regard. One, how important is that temperature constraint? I know in the US they're more focused on the temperature constraint than they are in the quantity, that it's the quality or the temperature. With climate change, the temperature of the stream's going to rise and they're not going to be able to emit. So I was wondering how important that was. The other question kind of around that is that generally I thought agriculture was at the end of the pipeline. So it wouldn't be that agriculture would get the water first and then people would get power later on. No, they get their power, and then if there's some left, they'll irrigate. Anyway, that was interesting.
Yes. You are asking the right questions, I have to say. So starting with your last question, I think how the water will be prioritized, it's highly uncertain. So in this case, energy came first and energy came last. So everything is in between, is possible in between. It's quite simple for the global perspective, and I know that there are, from river basin management, that there are different kind of priority settings. With regards to water temperature, water temperature plays a role, that's correct, and in some areas it's even more important than it is, for example, in the quantitative terms, that's correct. But I found out in the study that of an higher importance is the environmental flow provision. And nobody knows about those exactly, and we try to bring in a methodology that because we used a monthly based kind of water stress, so to say, that we would like to keep the high and low flows for the E-flow as well, and not just saying we use Q90 for E-flow. And I think this is now more important in that study. And the other one is what I know, for example, from Germany, although there is the constraint on the water quality, the power plants get always exemptions.